And welcome to today's webinar, GNSS Anti-Jamming and Anti-Spoofing Technology Explained, brought to you by GPS World Magazine and our sponsor of the event, Calian. I'm Alicia Lopresti from North Coast Media and GPS World, and I will be your event manager for today's presentation. At this time, I'd like to get you comfortable with our console and the ways you can participate during today's presentation. Please notice the Q&A panel on the right side of your console. If you have a question, type it in the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end during the Q&A portion. Questions submitted during registration have already gone to our speakers and may be covered during the live event. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and our technical support team will personally assist you. At this time, I'll turn the presentation over to our first speaker. Take it away, Mo.
Thank you, Alicia. Hello, everyone. I'm Mohammed Amara, an antenna and RF engineer at Calian GNSS. And my part of the webinar will focus on GNSS jamming. I will discuss the different types of jamming and how they impact system performance, as well as methodologies for jamming detection and mitigation. Let's start by reviewing the main components that make up a GNSS system. The first block is an antenna and RF front end. The antenna receives signals from space, and then bandpass filters isolate the required GNSS band and suppress any out-of-band interference. Low noise amplifiers then boost the power of the signal without adding too much noise. So in this way, the RF front end sets the noise figure of the system, which has a direct impact on the carrier to noise ratios and eventually on positioning accuracy. Next comes the GNSS receiver, which converts the RF from the antenna and RF front end to an intermediate frequency, and then performs analog to digital conversion with an ADC. There's also an automatic gain control loop that controls a variable gain amplifier to adjust the power for optimal ADC performance. After that, in the digital domain, the receiver performs signal acquisition and tracking, and finally computes position, velocity, and time, or PVT, for the user. And when we talk about GNSS jamming, we're referring to signals that have frequencies that fall within the GNSS band. These are signals that, if they're not properly mitigated, will make their way into the antenna and through the front end and into the receiver, and they can cause degradation to the performance of the system, or they can deny the receiver the ability to calculate PVT. And jamming is mostly intentional, but it can also happen from faulty equipment or from intramodulation of out-of-band interference. And as you can see on this map, jamming is prevalent in many parts of the world, and it's expected to get worse in the future. And jamming can be classified into two types, which are narrowband and wideband. And these are essentially classifications based on how the bandwidth of the jamming signal compares to the GNSS band. Jamming is classified as narrowband when its bandwidth is significantly smaller than the GNSS band. Examples include continuous wave or pulse continuous wave. As you can see on this plot, the bandwidth of a continuous wave signal is significantly smaller than the highlighted bandwidth of L1 and E1. On the other hand, jamming is wideband when its bandwidth is a significant portion of the GNSS band. An example is wideband noise, which raises the noise floor of the system and makes it harder for the receiver to acquire the satellite signals. Another example is chirp jamming, which is essentially a continuous wave that is swept in frequency over a duration of time. And in the frequency domain, it appears as a wideband signal, as you can see in the middle plot. And in this plot, I'm showing two examples of chirp signals, one with a 10 megahertz bandwidth and one with 20 megahertz, both of them centered at the L1 frequency. And the more sophisticated wideband jamming is one that matches the spread spectrum of the GNSS signal. An example is binary phase shift keying, or BPSK, for GPS, or binary offset carrier for Galileo. And on the graph on the right, I'm showing two examples of BPSK signals. The first one has a chip rate of 10 megachips per second, and that matches the spread spectrum of the L1 PY signal, whereas the second one has a chip rate of 1 megachip per second, and that matches the spectrum of the L1 CA signal. So even though the end result of jamming is to cause degradation to the performance of the system, it can impact the components of the GNSS system in different ways, which then leads to the performance degradation. The first components that get affected are the low noise amplifiers in the front end. When high power comes into the system, these amplifiers can saturate, and that generates spurious harmonics and decreases the gain of the front end. And this ultimately leads to a distortion in the useful GNSS signal within the band. The next components that get affected are the variable gain amplifier and analog to digital converter in the receiver. These components can saturate in a similar way to the LNA, but even if they don't saturate, the AGC will reduce the gain of the variable gain amplifier when higher power enters the system, which will basically reduce the power of the GNSS signal and cause a reduction in the carrier to noise ratio. And with low carrier to noise ratio, the acquisition stage will struggle to find the correct correlation peak between the received signal and the local code. So pseudo-range measurements will be degraded, and phase measurements will also be impacted with higher cycle steps. So when jamming is present, positioning accuracy will be degraded, and in the worst case, the receiver will track too few signals to be able to calculate any solution. So how do you know if you're being jammed? The easiest way is to look at the output of the receiver. If the C over N knots are lower than expected, or if you're tracking fewer satellites, that's an indication that jamming is present. For example, on this plot, you can see that under nominal conditions, signals have C over N knots between 40 and 50 dB hertz. So if you see a sudden drop in the C over N knots, that indicates that jamming is present. Another way to detect jamming is to observe the behavior of the automatic gain control. So normally, the AGC will only change in response to changes in the thermal noise of the system. So if you observe a sudden drop in the AGC, that means that a higher than normal amount of power has entered the system, which is an indication of jamming. You can also monitor the spectrum output from the antenna or the receiver. So typically, a spectrum in the GNSS band is only noise. So if you're measuring higher power in the GNSS band above the noise floor, or if you can identify waveforms that should not belong in the GNSS band, in this case, a chirp and a continuous wave, that indicates that your system is under a jamming attack. So if you are being jammed, how do you mitigate against jamming? Well, the best way to suppress jamming signals is right at the antenna before it enters the receiver. This is especially true for wideband jamming because it's very difficult for the receiver to deal with it in the digital domain. Using antenna arrays, we can create nulls in the antenna radiation pattern and direct those nulls towards the jamming sources to suppress power coming from their direction. And the way this works is by controlling the weight of each antenna element so that jamming is mitigated at the combined RF output from the multiple antennas. The first technique is to design fixed reception pattern antennas, or FERPAs. These antennas are also sometimes referred to as low elevation angle nulling antennas, or LENAs. And the reason being is that they form a fixed null, typically at a low elevation angle, to mitigate near horizon jammers. The second technique is to design controlled reception pattern antennas, or SERPAs. And these antennas can create adaptive nulls that can mitigate jamming anywhere in space and not just near horizon. The GNSS receiver can also help mitigate jamming, especially narrowband jamming. The receiver uses techniques such as notch filtering and pulse blanking, which are implemented before the acquisition stage to mitigate against narrowband jamming. And now I will give you an overview of the line of resilient anti-jamming antennas that we've developed at Calian. The first is the AJ979XF+, which is a two-element low-elevation angle nulling antenna. The AJ provides triple-band GNSS coverage, as well as jamming mitigation within those bands. With the AJ, we create a fixed null at a low-elevation angle that provides 20 dB of mitigation of near-horizon jammers. This antenna also has our XF+ front end, which provides 80 dB of out-of-band suppression, as you can see on the plot on the right. And it also provides 50 dB of isolation between the upper and the lower bands. And what this isolation provides is an extra layer of resilience. So if one band is jammed, the other band can still function and provide a useful, undistorted GNSS signal to the receiver. Our next solution is the CR8894SXF+. This is a 4-element SERPA that provides dual-band GNSS coverage and jamming mitigation. The SERPA is lightweight, and it can be powered directly from most commercial off-the-shelf receivers, and it provides 20 to 40 dB of jamming mitigation, depending on the type of jamming and the number of jammers. The SERPA also has our XF Plus front end, so it benefits from the high suppression of out-of-band interference and the band isolation. With the SERPA, when there is no jamming or under nominal conditions, the radiation pattern is a typical omnidirectional pattern with upper hemisphere coverage. But the moment jamming is present, the SERPA can detect the presence of jamming, and it adapts the radiation pattern by creating a null directed towards the jamming source to suppress the power coming from the direction of the jammer. And with 4 elements, we can create up to 3 nulls in the radiation pattern per band. And this is an example of an adapted radiation pattern with 3 nulls. Our next solution is the CR7712EXF. This is a 2-element single-band embedded SERPA. It's super lightweight and also has very low power consumption. With this SERPA, we can create an adaptive null that can be scanned in the plane along the 2 antennas. And here I'm showing 3 examples of nulls that we can create. And in this case, they scan in the vertical direction. With this SERPA, we can get 20 dB of jamming mitigation. And we also use our XF front end, which provides the 80 dB of out-of-band suppression. So what does mitigation mean? Suppose that you have a system that uses an antenna which doesn't provide any mitigation. And let's say that this system can operate at a certain distance away from a jammer. But if that system gets any closer, then it will fail and it will not provide the user any PBT. Now, if you replace that antenna with a 2-element LINA or a 2-element SERPA that have 20 dB of mitigation, then your system can get 10 times closer to the jammer and still function. And if you replace it with a 4-element SERPA that has 30 dB of typical mitigation, then you can get 30 times closer to the jammer and still have a valid PBT solution. So what this means is that higher mitigation allows your system to get closer to the jammer and still maintain functionality. And now I will hand this over to Sunil to discuss GNSS spoofing.
Thanks, Mo. So in this section of the webinar, we'll give a brief introduction to spoofing and mitigation approaches. So what is spoofing? Well, it can be defined as a malicious attack in which fake GNSS signals or a signal are or is broadcast. GNSS receivers acquire and track these fake signals the way that Mo has described, but using these fake signals, the result is incorrect positioning, navigation, and timing solutions. So spoofing, if we look at this, this little figure here, spoofing relies on the fact that the GNSS signals are very weak when they arrive from space. So we see the green, the green actual signals. And in blue, the blue X is the actual user position. But if we add a spoofer, the spoofer typically is on the ground or near the ground, and that signal's a fair bit stronger. And so the spoofer, when it generates these GNSS-like signals in close to the receiver, it's much strong. These signals are much stronger. The receiver ends up acquiring and tracking those signals, and we end up with the red position, the spoofed user position. So unlike jamming, which could be accidental or intentional, spoofing is intentional. And in many national jurisdictions, spoofing is illegal, and spoofers to generate the spoofing signals are illegal. So what are the different types of spoofing? There is meaconing, in which we can record the GNSS signals and then rebroadcast them at a later time or from a different location. And this is the simplest form of spoofing. So it is retransmitting the actual GNSS signals, but at a different time or different location. There are so-called carry-off attacks and different types of them, where software-defined radios, SDRs, are used to generate and then transmit GNSS-like signals. This can be done asynchronously, where there's a transmission of such a signal that's out of time sync. And the result would be, if the receiver would be tracking actual signals, then start tracking these spoofing signals, and we would see a jump in the PNT solution. There's more sophisticated versions, or synchronous carry-off attacks, where the fake signal is transmitted to look very similar to the broadcast signal, and then those signals are slowly varied, and we'll see a gradual drift of the GNSS or the GNSS-based PNT solutions from the correct one to the slowly drifting spoofed one. And this is all done, this can be done through, again, software-defined radios, and they can be used to generate and transmit custom GNSS signals, so ones that are even more varied. So why is there spoofing? Why is there this intentional degradation or forced change to the solutions? Well, we can classify them in a number of areas. One, for warfare, where militaries, and this is a primary use, could divert enemy assets or shield one's own assets. They can be done for criminal purposes, especially in areas of marine and land vessels, to hijack these vessels by spoofing their GNSS-based route tracking. Related can be used for fraud, and this we see this in the transportation sector, where drivers or organizations fake locations or bypass geofencing in order to avoid labor or increase illicit profits. And finally, for privacy, for some different purposes, such as games or in spoofing apps. So how prevalent is spoofing? Well, unfortunately, it's becoming more prevalent, and we see this in the news. So we, of course, go back to war zones, and we do have a number of conflicts going on, Ukraine, down in the Black Sea related, in the Middle East, parts of Southeast Asia. In commercial aviation is another area that we've seen some significant increases in spoofing. One report estimated that in 2024, there was a 500% increase in aviation spoofing incidences, peaking up to 1,500 daily incidences. Some hotspots in India, in the Middle East, and in Eastern Europe, and also in commercial marine areas, where in 2025, one report estimated over 10,000 vessels reporting spoofing effects just in the second quarter. And we have hotspots, as we'd imagine, Strait of Hormuz, in the Baltic, in the Black Sea, and the figure at the top right shows one map of an estimate of some spoofing events across the globe. So what can we do about spoofing? Well, we can classify the mitigation methods from the antenna down to the measurements. So at that top layer at the antenna, the next layer in terms of signal authentication, then the analysis of the signals in the receiver, and then monitoring at the measurement level. So at the antenna, one option is to have a multi-antenna system, because if we have a single spoofer or even multiple spoofers at fixed locations, it will result in the spoofing signals arriving from the same direction. So if we have multiple multi-antenna array, we can determine direction of arrival to determine the direction and the existence of a spoofer that is not coming from the actual signals from space. Another option, and Mo talked about this, is using a controlled reception pattern antenna, the way that he described it, with the expectation that the spoofing signal is being transmitted and received at a much higher frequency or being received at a much higher frequency than the incoming actual GNSS signals. Beyond the antenna, we can look at signal authentication. And the original version of this, of course, was with GPS AS, GPS anti-spoofing, it's a modulation to the PY code, the output PY code, and the only way to access that modulation and decrypt it is with military-grade receivers. That has progressed in development to the GPS encodes that we have now. For civilian GPS signals, there's GPS Chimera, which is an experimental process, which stands for Chips Message Robust Authentication. And it's an authentication layer for civilian GPS signals that's being developed so that we can authenticate the signal to know that's the actual signal before using it in the receiver. Galileo has the OSNMA, the Open Service Navigation Method Authentication, and it's an initial operational capacity at this point to have this authentication layer authenticate the message before using it for Galileo signals. There are others, such as QZ, SAS. Galileo also has their PRS system. And some commercial service providers have added authentication layers as well. Within the receiver, there are a number of approaches that exist to monitor for and try to detect spoofing. The first is power, that again, if the expectation is that the spoofer is at a significantly or noticeably higher power than the actual signals, that we monitor for rapid jumps in SNR. We can also monitor the Doppler and look for inconsistencies in what is a very predictable phenomenon. Also, when we're carrying out the correlation process in the receiver, we can look for multiple correlation peaks, the authentic one, and then others that are delayed or have higher amplitudes. And finally, we can look at unexpected jumps in positioning and time coming from the output of the measurements, which leads us to the last classification or class of mitigation options, and that has to do with looking at the measurements themselves. Many of us know receiver autonomous integrity monitoring, or RAIN, where we look at the output measurements in the least squares process and look for inconsistencies, that are outliers in the residual measurements to detect potential spoofing and remove those measurements. If we have the benefit of multi-frequency and multi-constellation antennas and receivers, we can also look at the individual frequencies and individual constellations to find redundancy there if the spoofing is occurring on particular frequencies or for particular constellations and not the others. And finally, we can look at non-GNSS sensors. Accelerometers and gyroscopes are not affected by radio frequency interference. Therefore, if we have an independent inertial solution, we can use that to compare against GNSS displacements and determine if there is spoofing occurring on the GNSS. So with that, I'll stop that brief introduction and pass things on over to Ian.
Thanks, Sunil. My name's Ian, and I'm an antenna designer with Calian. And today I'm going to discuss the evaluation of our resilient GNSS antennas from design through to field testing. So the first part of our GNSS antenna that sees the signals, sees the jamming, is the front end. So I'm going to discuss our XF Plus architecture, which is used in both our SERPA antennas as well as our low elevation angle nulling antennas. What the XF Plus filtering allows the LNA to do is that we have high out of band rejection over 80 dB and also very high isolation between the bands. This allows the signal fed through each band and each beamforming network to be totally isolated, and jamming on one band will not impact jamming on the other band. The very sharp filtering is also useful for getting rid of known sources of interference that are present everywhere in the world. So as an example here, we have some communications bands that are highlighted in yellow that are very close to the upper GNSS band. And because of the sharp filtering that these front ends employ, we are able to mitigate these, and so these signals are not passed into the receiver, and then they do not interfere with reception. After we characterize the performance of the LNA, we start to characterize the performance of our antennas. To do this, we first measure the radiation characteristics of the antennas. We do this in our anechoic chambers. On the left, it is an example of an anechoic chamber we use to measure radiation patterns. The antenna under test in this case, in the left image, is located at the center of the image, and around the antenna is a series of transmit probes that can measure the far field over elevation. The antenna is on a pedestal that is able to rotate about the zenith of the antenna, and this allows us to measure multiple azimuth cuts. The example on the right is an image of our AJ979 XF Plus, one of our FERPAs, or our low elevation angle nulling antennas, where the phase center of the antenna under test is located at the phase center of the chamber, as illustrated by the red laser crosshair. This allows us to measure both the magnitude and the phase of the radiation patterns, which helps us to fully characterize it and fully understand the performance of the antenna. Once we start looking at these patterns, we'll start looking at the pattern of a standard GPS antenna. So starting with our TW1889XF, which is just a single element ceramic patch antenna. This has a general characteristics of a good GNSS antenna. So the plot, I'll explain. The black traces show the copolarized or the right-hand circularly polarized signals, whereas the red traces show the left-hand or the cross-pole signals. There are multiple traces here, and each trace represents a different azimuth cut. The first thing we look for in a good GNSS antenna is a strong lobe at zenith and gentle roll-off towards horizon to be able to receive low elevation satellites. This can be seen here by only about 10 dB roll-off from zenith to horizon. The next feature we look for is that the multiple azimuth cuts are all very similar. So the reception of the antenna is radially symmetric and can equally receive satellite signals regardless of the antenna's rotation. The final main thing to look for here is the polarization rejection ratios. Sorry. So here we have a very strong cross-polarization rejection between the black and the red traces. This is important for multipath mitigation, where when the GNSS signals bounce off anything reflective, the handedness of it flips, and then you get multipath, which degrades the solution quality. Strong cross-polarization rejection will help to mitigate these types of signals. Next, I'll talk about our two-element SERPA, the CR7712EXF. As Mo mentioned, our SERPA antennas have a nominal mode, which they operate in when there's no jamming. So these radiation patterns are optimized for good GNSS reception. So again, we have a strong copolarized radiation pattern with a peak at zenith and gentle roll-offs towards horizon. However, as you may notice, there is more difference in the azimuth cuts as the gain rolls off differently depending on how you look at the antenna. This is due to the physics of the antenna, as it's asymmetric, it's radially asymmetric. So if you were to look at a radiation pattern in the X plane or in the X direction, as shown by the coordinate system on the antenna, it's much narrower compared to if you look at the orthogonal azimuth direction, which is much wider. However, regardless of this, the cross-polarization rejection is still very good, and this antenna is still good at receiving GNSS signals. It's just important to know when installing it and when using it, what the pattern looks like. Next is a LINA radiation pattern where there are strong nulls at horizon. And here we measure that in the copole as a very deep null, and which is that just above horizon around all of the azimuth. This has very strong cross-polarization rejection in the main lobe. And finally, turning to our 4-element SERPA, the CR8894SXF+ in its nominal mode, we have, again, a gentle roll-off from zenith to horizon for the copolarized gain, very strong cross-polarization rejection. And because this array is more radially symmetric than the 2-element, we have less variation in the azimuth cuts for the magnitude variations of the gain. After characterizing the nominal radiation patterns of the SERPA, we measure the null-forming radiation patterns of each SERPA. To do this, rather than using Cartesian plots, we use polar plots to make it more easy to visualize what's happening. In this example, this polar plot shows the copolarized right-hand circular gain, and the color plot or a color scale is used to show areas of high gain and good GNSS reception, and darker colors for low gain and good mitigation in nulls. So in this specific example, we requested the unit to set a null at the location of the red X, and the null passes through it and provides over 30 dB of mitigation in this specific case. And there's a main lobe for GNSS reception in the opposite direction that is unaffected by the GNSS null. Next, our 4-element SERPA can set up to 3 nulls per band. So we measure, characterize radiation patterns in all these cases. Here's an example of it setting 3 nulls, again, all shown by the red X's, the deep nulls. We check that they match the desired location. We check that the mitigation meets the spec, and that there is still a strong main beam to receive the GNSS signals away from the location of the nulls. After we've fully characterized the antenna radiation patterns, we characterize and develop and optimize our beamforming network and algorithms. To do this, we use guided simulation tests to help expedite the design process. For this, we have a 4-port GNSS jamming and GNSS signal simulator that generates 4 phase coherent signal outputs that replicate what the output of the antenna array would look like feeding into the beamforming network. This allows us to just test the beamforming network in a controlled environment. To characterize the beamforming network and the quality of the anti-jamming solutions we get out of it, we connect the RF output to a GNSS receiver to monitor the GNSS quality, and we read the output of the SERPA over serial to a PC to log and understand what the unit is doing and why it makes the decisions. As a point of reference, we connect one of these jamming and GNSS simulated signals to a reference LNA to a GNSS receiver running the exact same configuration. This allows us to be able to compare 2 things from the same type of GNSS receiver so we can understand how the beamforming network is improving on the signal quality given to the receiver. As a first example here, on the left, you can see a sky view, which shows a series of satellites, and these are the satellites, the simulated satellites that we are receiving, and then a jamming signal located west of the unit by the red radiating symbol. The unit in this case is located at the center of the polar plot. The jamming signal in this case, we're varying the power, so we're varying the jammer to signal ratio. The jammer is again a single jammer, and it's a wideband, white Gaussian noise type jammer. So we can see as we start with a low jammer to signal ratio, which is shown in the first case as a J over S of 30 dB, highlighted in pink, we can see that both antennas are impacted by the jamming, or the receivers are both impacted by the jamming. The SERPA and the reference antenna perform similarly, with the SERPA performing slightly better. As the jammer to signal ratio increases, however, the usefulness of the SERPA becomes apparent. As the jammer to signal ratio is 40, 50, the SERPA's average C over N knots, which is the metric we're using here, which I didn't explain, is with the average C over N knots is the average carrier to noise ratio from each of the satellites simulated. So in this case, it's a single band at a time, and we're looking at just Galileo and GPS, so L1 and E1 as an example. And as we have jamming, we can see that the carrier to noise ratio decreases more for the reference antenna compared to the SERPA, as the SERPA is able to provide mitigation to mitigate the jamming signal before it reaches the receiver. This is especially apparent once the jammer to signal ratio reaches 60. The carrier to noise ratios averaged for the SERPA are still going down from the no jamming cases. However, the reference antenna has no satellites available for the solution for the 60 dB and the 70 dB jammer to signal cases. We also evaluate our SERPA because it can do 3 nulls per band. We set 3 jammers per band and evaluate how it performs there. This example also goes to show why a SERPA type beamforming network is needed to help the receiver. So here we have 2 cases. The first one highlighted in pink is a CW signal, so a continuous wave signal with a jammer to signal ratio of 55 dB. And both the SERPA and the reference antenna perform similarly. The SERPA performs slightly better because it's providing some mitigation before the signal gets to the receiver. But the reference antenna and receiver are still able to function because the receiver can apply a notch filter and filter out the jamming signals. Once a 20 megahertz wide AWGN signal is applied, as shown in the second column, the SERPA's average carrier to noise ratios are degraded. However, a usable solution is still given from the receiver. Whereas the reference antenna, the number of available satellites drops to 0 and no solution is usable. Once we validate our beamforming networks in a guided situation and we validated our antenna, we combine the 2 together and we measure how the antenna responds in a radiated jamming environment. So this is done in an anechoic chamber, which is a very clean environment from an RF point of view. So here we have our antenna under test, in this case our CR8894 SXF Plus, located in the center of the chamber on a mast that is able to rotate as shown by the red arrow. In this specific example, we have 3 jamming antennas located around the horizon relative to the antenna, approximately 90 degrees apart in azimuth each. These antennas are connected to a series of signal generators that are able to broadcast at both the upper and lower band out of each antenna, as well as multiple different modulation schemes. This allows us to fully test how it would go and how the antenna would function with real-like jammers. So to understand what this looks like and to try to visualize it, we have a pictogram on the left, which shows the orientation of the SERPA relative to our 3 jammers, which are currently off in this example, and our Sentinel Monitor client software, which displays how the SERPA is functioning at any given time when it's connected. So currently with the no jamming, as seen here, there's no mitigation. The SERPA detects no jamming, and the ambient power levels are low. Once the jammers turn on, you can see that the SERPA detects jamming at both bands and applies mitigation. So again, these jammers are turned on at L1 and L2, so we're setting nulls in both directions. You can see the increase in ambient power as well as the estimated mitigation from the SERPA. As we rotate the SERPA, it's able to continue to track the nulls and continue to provide good mitigation. And as we further rotate, we're able to see how the nulls follow. This, again, is a very clean environment. So in a more real-world environment with uncontrolled reflections and other install differences, the direction finding will not be necessarily as clean as this. After measuring in an anechoic chamber and understanding the null shape and the ability to set mitigation, we measure the actual GNSS performance. We do this on our reference station here in Ottawa, where we have a beam with a known location that we install the SERPA antennas on, and a reference antenna, in this case our Verichoke, which is a high precision antenna that allows us to know where the antenna is relative to the reference antenna. Since there's no jamming at our location in Ottawa, we force the SERPA to set nulls in given directions, and then we analyze how the GNSS performance is degraded. So as a first example, we set a null on the southwest of the SERPA at horizon. So the SERPAs are oriented to the north mark of the SERPA is aligned with true north, so we can figure out where the null is in real space and how it's impacting the GNSS signals. So this is comparing it to the reference Verichoke, which is a very high quality GNSS antenna. And we're only comparing GPS L1 and L2 and Galileo E1 and E5B to be able to make sure to ignore any differences in filtering between the two different antennas. So as we can see, when we're setting a null, the SERPA has a lower carrier to noise ratio compared to the Verichoke, the reference antenna, and the number of satellites is slightly less because the null is somewhat blanking some of the satellites. We also measure how the position of the SERPA apparently moves when we set the null. So again, we know where it should be. We calculate a displacement vector from that known position to where our new solution is, and the plot at the bottom presents the magnitude in the null. As we set two nulls, again, the carrier to noise ratio is still around 40 dB hertz. And in this specific case, because there were no satellites going through the region that was being nulled during this time, the number of satellites is unaffected between the Verichoke and the SERPA. Again, the PCO change is less than 10 centimeters. And finally, a case with three nulls, we see some loss of satellites due to the nulling, but the movement of the PCO in magnitude is less than 10 centimeters. Finally, to actually characterize how our antennas work in a more real-world example, Jammer Test has been an invaluable resource for this. So we've attended Jammer Test in 2024 and 2025. And here's some pictures of our setups. So in the middle top picture, we have an example of our GNSS antennas set up on tripods. And then there's a single jammer located on top of the mountain in the distance. The right image shows a similar setup from the other view. There are other locations, other jamming tests using cars, using multiple jammers. GNSS antennas can be put on planes as shown in the bottom right image. So to start with our jammer test results, we're going to start with a strong single jammer source. So here's an example of a picture from Jammer Test of their antenna array that is used to generate the jamming signals. This is again on top of that mountain, and our antennas under test are located in the middle of the image near the beach. So this jammer was a very strong jammer and was able to provide 80 dB of jammer to signal ratio. The first examples on the left, we have our SERPA, our CR8894 SXF Plus, compared to a reference antenna. The first example has C1 jammers at multiple bands. So the SERPA is providing over 30 dB of mitigation, but the GNSS receivers used are also able to notch out the CW jammers. So the SERPA performs better than the reference antenna during the jamming. However, the difference is not as drastic as when there's a wideband modulated signal. On the right, we can see an example of a PRN signal which replicates the spectrum of a GNSS signal. In this case, the receiver's notch filtering is unable to filter it out, and the mitigation of the SERPA is necessary for a solution. So here we are able to still provide a solution, whereas the reference antenna is unable to track any satellites. As another test with multiple jammers, there was a situation where we set up with multiple jammers positioned around us, and we understood the effect of multiple jammers, how the SERPA was able to set multiple nulls to mitigate this, and the impact of spoofing in the same situation. So in this case, the SERPA was located, or the antennas under test were located at the center of the setup, and there were 3 antennas spaced around the SERPA, each radiating a wideband signal. And we can see here that initially in the pink color, the salmon color, the jamming causes a reduction in the average C/N naught, but we're able to still track at minimum 8 satellites across the whole time with a very strong jammer to signal ratio of 85 dB for this chirp signal out of the 3 jammers. And then starting at about 1310, a high power spoofer, the power starts to ramp on that. So you could see this because the average C/N naughts start to go up as the apparent signal or the spoof signal takes over from the weaker GNSS signals. This results in the darker pink color where the antenna is being spoofed, the receiver knows it's being spoofed, and the apparent jammer to signal ratio is less than, or drops to 55 dB. So in summary, jamming is an interference worldwide. Today we've discussed two GNSS antenna technologies to mitigate jamming, both controlled reception pattern antennas that can adapt to scenarios to set nulls to mitigate jamming, and low elevation angle nulling antennas to mitigate jamming as well. Finally, GNSS receivers have methods to mitigate some types of jamming, but the antenna is the first line of defense. GNSS spoofing. Spoofing is mostly seen in conflict zones, which spoofing tricks the receiver by broadcasting false information to give incorrect PNT results. SERPAs and LINAs can help if the spoofing power is high enough, where the SERPA detects it as jamming. GNSS receivers have methods to detect and report spoofing, so it knows that the solution is not usable. And finally, broadcast ephemeris messages can be used to authenticate the GNSS signals. Finally, it's very important to be able to characterize, evaluate, and test all resilient GNSS antenna technologies. We do this in the lab with jamming and spoofing simulations. We do this in anechoic chambers where we can create the full system and provide jamming signals. But real-world testing, like at Jammer Test in Norway, is the most important for testing resilient GNSS hardware. Thank you, and I'll pass it back to Alicia.
Thank you, everyone, for a great presentation today. Now we're going to jump into some questions we received during registration and a couple from during the presentation. When under a jamming attack and using a CRPA antenna, by how many centimeters does the antenna's phase center position change? I am using RTK with centimeter level accuracy and need to know this value.
Yeah, I can answer that. So we do not have an answer for that under jamming. However, we know that under jamming, the SERP is able to set nulls, and we can test this by setting the same nulls in a known reference station. As we've shown in general, the total movement, once it's found the solution in the new null, is less than 10 centimeters for almost all cases, but we can discuss further after.
What are the limitations of the CRPA?
So if we're comparing the SERPA to a standalone antenna, there's of course a trade-off to having jamming mitigation. One thing you have to account for is the added weight of the SERPA. Of course, the SERPA will have multiple elements, so it's going to weigh more than a single antenna. When the SERPA forms a null, there's also a risk of losing satellite signals in the direction of the jammer or where the null is placed. So you might be tracking a fewer number of satellites than a single antenna, but of course, under jamming, the single antenna will not be able to track any satellites. So it's a worthwhile trade-off. Yeah, so these are the trade-offs that you can account for.
How much jamming and spoofing protection is or will be provided to the government and military users with adoption to the GPS M code and the Galileo PRS?
Well, I can take that one. I mean, they were designed for these purposes. So on the spoofing side, with the authentication for both the M codes and PRS, they're designed for that requirement for authentication. So they will be able to avoid the spoofing or a fake signal. In terms of jamming, there will be with stronger signals, especially with the M codes, there'll be a reduction to jamming, but of course they can still be jammed. And I don't know if Mo or Ian want to add anything on the jamming side.
I think it depends on the receiver that you're using and the jammer to signal ratio. But ultimately, with more power, anything can be affected.
When designing a multi-GNSS AJ/AS system, how are you able to isolate interference on one band within the system so as to not couple over to the other bands?
I can answer that. Yeah, you go ahead, Ian. Okay, so Ian mentioned in his slide that we isolate the bands so that they don't share any components. So that helps in isolation. There's also other techniques that we use, such as RF shielding, to reduce the mutual coupling between the bands. We also use custom designed filters so that the filter has good response in the pass band, and on the other band, it has good suppression. I don't know if there's anything that you want to add, Ian.
Okay, excellent. All other questions will be forwarded to our speakers for follow-up. Thank you, Callian, for a great presentation today. Now we will wrap up the live event. Thank you for attending GNSS Anti-Jamming and Anti-Spoofing Technology Explained, brought to you by GPS World Magazine and our sponsor of the event, Callian. A recording of this webinar and other upcoming webinars from GPS World will be posted to gpsworld.com/webinars. Thank you for joining us today, and we hope you'll tune in again soon for more great webinars.